Hi everyone, so in this video I would like to discuss the Reynolds transport theorem, which is named after Osborne Reynolds, that creates a connection, a very important connection between a system and the control volume view. So you already have an experience with control volumes. We have talked about that in the derivation of the momentum, macroscopic balances of momentum and mass. So these are fixed regions in space that of course can be crossed by mass through their surfaces that are called control surfaces. While on the other hand, the system is a quantity of matter of fixed identity. So the mass cannot cross its boundary, but the system can change shape and size and actually move with the flow, but still keeping always the same amount of mass. So you probably realize that this is similar in a way to the relationship between a Lagrangian view of a system. So the person in the boat that measures the concentration of a pollutant in time but moving with the boat, and the person that is standing on the bridge measuring the variation in time. So there is a link between the RTT and the material derivative that we will discuss in the end. To look at this problem from a mathematical point of view, we have to define, let's say, a problem of study. And so what we consider here is a region of a flow. It's a diverging region. What you see here are streamlines of the flow. So these are streamlines. And what you see, of course, is that at each cross section between these two streamlines will be characterized by a uniform flow. In particular, we consider a section 1 and 2 here that define our control volume. So this is region in rows. This is our control volume. And by definition, we say that at time t, the system and the control volume are the same thing, namely that they are completely overlapped. Then, of course, as t goes by, the time goes by, so you have a delta t which passes. What we have is that some mass will actually flow from the left to the right, and so the system will move by definition with the flow. And because of that, the system and the control volume will not occupy anymore the same region. In particular, you see from this schematization that the system will not occupy anymore the region 1, which is partially overlapped with the control volume, with the fixed control volume, but will cover a new region that we indicate here with 2, that of course is not contained in the control volume. So in other words, at the time t plus delta t, the system will be associated to the region which is the control volume minus the region 1, which is not covered anymore, as I said, plus the region 2, which is newly covered by the system. Okay, so here I will put plus 2. Great, so now the question that we ask is what happens to a property B? So an extensive property can be mass, can be momentum, energy. Can be what happens to this property, in particular, what is the relationship of this property in a system and in a control volume view? Of course, B can be expressed as the product of the intensive property times the mass. And what we can say here is that at times t, of course, so we have a first equation at times t that says that, of course, the system and the control volume completely overlap, and so, of course, there is no difference between the property of the system and the control volume by definition. Now, at times t delta t, things are different because now what happens is that the system, as we said, has moved to the right. It doesn't cover anymore this region 1, but it does include a new region, which is the region 2. And so what we can say is that a B system at times t plus delta t will be given by the B of the control volume at times T plus delta T, minus the B of region 1 at times T plus delta T, plus the B of region 2 at times T plus delta T. Okay, so when looking at these two equations, what we can do, of course, it seems pretty normal and pretty straightforward to think about that, is to take equation 2 minus equation 1 and divide it by delta t. And so let's see what this actually provides. Okay, so if we do that, what we get is the following. So we have B system at times t plus delta t minus B system at times t divided delta t. This is equal to B control volume at times T plus delta T minus B control volume at times T divided by delta T plus, minus B in region 1 at times T plus delta T divided by delta T plus B in region 2 times T plus delta T divided by delta T. Okay? Okay, this is great. So we already get some ideas of what we can do with that. In particular, if we take a delta t that goes to 0, and we use the definition of the derivatives, what we can actually say is that we basically get the following expression. So we have a dB of the system on delta t equal derivative of B of the control volume in time, and then we have these two terms that we will express like this, and then we will discuss a little bit more in the following. So we call them flow rates of B coming in and flow rates of B coming out. So I think there is not much discussion to do on the first two terms. You see that if you take the limit as delta t goes to 0, this is simply the definition of the derivative. So I think these two terms are pretty straightforward. Now maybe there is some discussion to do on these two terms, and we can simply do that by looking at the expression of B1 and B2. So let's start with B1. Of course, I, and the same will apply, of course, also for B2. So what is the B that actually is now in region 1 after a time delta t from the beginning of the process? So from the time t where we consider that the two processes were the system and the control volume were overlapping. Well, we have some mass that has entered in this region because there was some flow passing through section 1. And so this B, capital B, can be expressed as the small caps B1, because the property passed through section 1, times the mass in region I at times T delta T. But what is this mass? Then the mass is simply the product of the density times the volume. And again, the density is the density of the fluid that went through section 1. Okay, so it's rho 1 times the volume in region 1 at times T plus delta T. Okay, but then what is the volume? And you see that the volume can be simply expressed by the length traveled by the fluid, and this is given by a velocity times the delta t. So the delta t that was between the original condition and the final that we are considering. So the time elapsed for the process. And of course we have to multiply by a section that will be the section of the cross section 1. Okay, so A1. So you see very clearly that if I take now the limit, what happened here? Okay, if I take the limit with delta t goes to 0 of B1 at t plus delta t divided delta t, I simply get this expression, so b1, rho 1, v1, a1, where of course you clearly recognize that this is the product of b1 times the mass flow rate in section 1. And of course you also understand that if your extensive property is the mass, then of course b will be 1, and you simply get that this is the mass flow rate crossing the section, which is quite straightforward, I think, in this case. So to actually summarize here, this expression b1 is simply rho 1 v1 b1 a1, and b out is rho 2 v2 b2 a2. Okay, so this means that we can actually rearrange the equation and write the equation in the following way. So we have a dB system over dt equal dB control volume over dt, and then we have minus b1 rho 1 a1 v1 plus b2 rho 2 a2 and v2. Okay, so this is the expression that we find for the problem at end that relates the property in the system with the property on the control volume. And of course you see that the property in the system will be equal to the variation of the property in the system would be that of the property in the control volume minus the flux of the flow rate of the property coming in from section 1 plus of course the flow rate of the property going out from section 2. Okay, so this is an expression that of course is valid for the specific case where we have one inlet and one outlet. So we have to consider that in general our problem might be more complex, and so one first let's say hypothesis that we might need to change is the following. We have considered a system which has one inlet, one outlet with the let's say with the velocity vectors that are always orthogonal, the direction of the flow that's always orthogonal to the control surface. But this is not always the case. You might have a control volume like this with different normals. You see there. This is the normal here, so the normal changes all the time, and then you might have different fluxes coming in with different directions, and so you have to in a way generalize this expression that we just derived for the mass flow rate. So in particular, what we can do, we can say, okay, the net flow rate of property B across the surface, which is of course the difference between what goes out and what comes in. Okay, this is simply given by an integral on the surface, so the integral on the control surface of the let's say the property, the intensive property, so rho small caps b times the velocity. So here I'm using the expression that we just derived for the flow rate of b, scalar product the normal, and then of course I have to multiply by the area. So by doing that, so by doing the integral, of course I'm considering all contribution across this control surface that we have here. And by doing this scalar product, I'm considering that, of course, the velocity vector might not be normal to the control surface at the point of entry. So here I have the definition of this flow rate. It's rho b v times the area. but I have to consider that the velocity vector might not be normal to the control surface at the point of entry, and so I have to consider the scalar product. So this is one first thing that we have to consider. The second one is the fact that it might be that the properties within the control volume vary or change. Okay, so this means that instead of just considering the extensive property BCV, I have to consider the integral on the control volume of rho B integrated in the volume. Okay, so this is just to take into account the fact that these properties within the control volume may change with the position. Okay, so with that in mind, I get to the final expression for a control volume. Okay, so now we have then the Reynolds transport theorem that can be, of course, shortened with RTT for a fixed CV. It's simply given by dB of the system over dt is equal to the integral in the control volume of rho d is partial derivative d over dt rho b dv. Of course, here I'm using the partial derivative because b might and rho might not only be dependent on time. Okay, plus control surface rho b v scalar n dA. Okay, so I am actually using the two expressions that we derived before, and we have the Reynolds transport theorem for a fixed control volume. And the interpretation of this, it's quite simple. It's the same as we have done for the simple one inlet, one outlet case. The variation of the system property in time is the variation of the system property in the fixed control volume, plus the variation due to the inflow and outflow of the property across the control surface. Now, we can also generalize this formulation by making the following consideration. So we have this property of the system, and we know that the system is of course changing in time, but it's always containing a fixed a quantity of matter of fixed identity, so always the same amount of fluid. So what we can actually do on this left hand side is that we can also expand the term dB system over dt to show that this is a property that is evaluated on a moving volume. And so this is a moving volume, so we have to use a material derivative, so it's a d over dt, and then we have integral on a moving material volume at time t. This is rho b dv, so this is the property in this volume, which again is moving with the fluid, but it's always containing the same amount of matter. And this is given by again the integral in the control volume of the integrating control volume partial derivative of rho b dt times dB plus the integral on the control surface of the property flow rate. So it's rho b v scalar n dA. Okay, now let's a little bit remember what we said about our system. So we know that this is our system at time equal t0, and we imagine that at this time, the system and the control volume are coincident. We have a certain flow, of course, here. So what we can think is that, of course, as we move in time, this will be the system at time t plus delta t, and maybe why not? This was the system at time t minus delta t. Okay, so we have a flow. We have that the system and the control volume are coincident for a certain time, as we said here, for a time t. Then the system is moving, and so it will partially overlap. You see it here only with the control volume at the time t plus delta t, and it was partially overlapping with the control volume at times t minus delta t. But at time t, the two actually are fully overlapping. So what does it mean? It means that at time t, the system at time t, the system and the control volume are coincident. It means that Vm of t is equal to the control volume, and Sm of t, so the surface of this material element of that contains always the same fixed amount of matter, will be coincident with the control surface. And so this actually means that the integral, the volume integral and the surface integral that we have on the right hand side of the Reynolds transport theorem can be evaluated over the Lagrangian volume and over the Lagrangian surface at time t. So what I mean here is that when we look at this equation, d over dt integral on the material volume, Lagrangian volume Vm, this is equal to the integral on the control volume of d rho b over dt dv plus integral over the control surface rho b v scalar n dA can be in fact rewritten considering that these two are equal to the control surface, the material surface and the material volume at time t. And so in the end, what we get is simply d over dt Vm of t rho b dv equal integral over Vmt d over dt rho b dv plus Sm of t rho b v scalar n dA. And so this is the final expression of the RTT. That, by the way, for the people that know the Leibniz formula for the differentiation under the integral sign, can be in fact be seen as the generalization of the Leibniz formula. Okay, so we have now, you see, an RTT form that is applied to a moving fluid element of fixed identity. So it's a fluid element that deforms and moves with the flow, but with always the same amount of mass, so which is not crossed anyhow by any flow rate. Okay, so we can actually rewrite this here because we are going to do some manipulation. So the final form that we get is the following. So what we are going to do with this formula here is that we are focusing on this term that you see here. In particular, we are going to use the Gauss-Green theorem to express this surface integral as a volume integral. This is also called as a divergence theorem, and so it's something that you probably know from your previous math classes. Basically, by applying the Gauss-Green theorem, we can simply express this surface integral with the scalar product as a volume integral with the divergence of this quantity here. So finally, this expression reads d over dt Vmt rho b dv equal, then we have only a volume integral, and then we have two contributions to that. So one of them is the same, it's the partial derivative in time of rho b dv, and then we have the divergence contribution that we are going to express in this way, plus the divergence of rho bv. Okay, and of course I have to then multiply by dv. So remember the transition from here to that, we use the divergence or Gauss-Green theorem. Okay, so now you're probably wondering what we can actually do with that. And so what I'm gonna show you before I close this video is the power of this Reynolds transport theorem to derive the conservation principles. And so we're going to do that for the continuity equation that, of course, we have already derived. So you know already what is the equation that you expect. So we want to derive again the continuity equation with the Reynolds transport theorem. Okay, so what we do is that we consider a system approach, and so we consider a volume of fluid of fixed identity, as we said before. So a volume which rotates, translates, deforms with the motion, but that contains, so deforms, rotates, moves with the flow, but which contains a fixed quantity of material, which basically means that it cannot be crossed by any mass flux, any mass flow rate, which mathematically can be translated into the fact that the scalar product between the velocity and the normal to the surface in each and every point of the surface is equal to 0 over the Sm of t as a function of time. Well, for this kind of problem, writing the conservation of mass, it's quite simple. we have said that this volume does not change its mass. So the variation of the mass for the system must be equal to 0. So what is the property we are interested in? The property here is the mass, which means that for the problem at end, B will be equal to 1, and so capital B is simply the mass. Okay, so we write our conservation of mass for the system, and this is simply d over dt, again material derivative because we have a moving element, integral over Vm of t, rho dv, and this is simply equal to 0. Okay, it's equal to 0 because by definition this volume element will not accumulate or lose mass. But then what we have to do is that we have simply to apply the Reynolds transport theorem that we just derived. And so we know that applying the Reynolds transport theorem will give us that d over dt of Vm rho dv is simply equal to what? To the volume integral of d rho over dt plus the divergence of rho v times dv. Okay, and so, and this is equal to 0 because we said that this derivative should be equal to 0. And so since this should be valid for every point in the control volume, we can simply obtain the final expression of the continuity equation, which is d rho over dt plus divergence of rho v equal to 0. So you see that with this approach, so by defining the conservation of mass principle for the moving element and applying the Reynolds transport theorem that we obtained here, we actually are able to find this continuity equation in a very efficient and fast way, without all the procedure that we were actually forced to do by applying, by considering the different fluxes across the surfaces in the cube. So you see the power of this approach that can be in fact used to make a very strong, to make a link between the system and control volume approach, but in particular can be used to find this conservation principle. And in fact, we will use this approach also for the derivation of the Navier-Stokes equations. Okay. Now you probably felt already that there is a strong, let's say, connection between the Reynolds transport theorem and the material derivative. Okay. And in fact, you are completely right, because in fact we could actually argue that the material derivative that we have indicated as d over dt is in fact a link between, as we said, a Eulerian description and a Lagrangian description. While the RTT, as we said, is a link between a system analysis and the control volume analysis. But so, by looking at this definition, we can certainly argue that, in a way, the Reynolds transport theorem is the integral counterpart of the material derivative. or in other words, that the material derivative is the differential counterpart of the RTT. So both are, in fact, bridges between Lagrangian concepts and Eulerian concept, but one of them is applied in a differential context, and the other one is applied in the context of differential equations. Okay, so with that, I will actually close this video, and so the next one will actually focus on the derivation of the Navier-Stokes equation using also the approach that we just discussed.